Earlier, we talked about telescopes, but we really only talked about optical telescopes. Remember that optical means something that you can see with your eyes. That's really all it means. I'm going to have to brag here. This picture was taken actually through binoculars. That right there is the Grail satellite, twin satellites that went to the moon. I got to go down there and watch this launch. This was from about 5 miles away. And I took the picture because I saw the kayak, and then later when I got home, there was a seagull in it. Didn't even notice that. So this is my iPhone being held up to the binoculars, which is why you get the cool round effect. I've always liked this one. Anyway, we're going to look at non-optical telescopes, no pun intended, because this gives us a whole new window or perspective on the universe. We talked briefly about how visible light and radio waves are what make it through the Earth's atmosphere. So these are the ones that get observed the most because they're the easiest to observe. Radio waves are not blocked by clouds or Earth's atmosphere. You can do it day or night. The nice thing is you can see these radio waves traveling through dust clouds in space, so it allows us to see further than other things. The bottom right image is a picture of Jupiter in the radio waves. You can see that it emits a lot of radio waves off the surface. This is from the magnetic field. In fact, the radio waves emitted off of Jupiter can be picked up with an AM radio. I have never done it myself, but I've seen videos where they have these weird sounds emanating from Jupiter, and you have to be very far away from regular stations, so out in the country, for you to tune in and notice that. It's pretty neat. So this image is of microwaves, and something that we'll talk about in a lot of detail is that the light from the beginning of the universe, the main event, the Big Bang, is still around, and it has been what we call redshifted into the microwave region. So this is the universe in microwaves. It is quite literally a baby picture of the universe. We'll get into that one quite a bit because this is like one of the most exciting pictures of astronomy. It looks like it, doesn't it? You're familiar with infrared. This is what you feel is heat, and it allows you to see things like star birth and new solar systems being formed. We can find objects in our own solar system that are hard to detect with visible light. You typically need to be high up in the atmosphere or in space to do that. So the bottom right airplane with the big hole in the side is the SOFIA telescope by NASA. It will fly up to really, really high, over 50,000 feet, I believe, and will take images of everything. So your workspace is where all those people are in the seats right there. Guess it's not as exciting as sitting behind a telescope, but this is the high-tech stuff. On the left, you can see Orion, and looking at it in infrared, you can recognize there is a lot more going on over there than you can see with the naked eye. So things like infrared and radio waves allow us to look at the universe and say, hey, what's going on over there? That's different. You can look at the universe in ultraviolet. So there's a comparison of a galaxy up above. You can see on the right-hand side would be regular light. That's an R, so I'm wondering if that's just red light, but they make it false image in blue. And then ultraviolet light shows that there's stuff going on there, like what's happening over on this side of the galaxy and on that side? Why is there nothing between those regions? It gives them more to look at. a shooting star that you might see across the sky. Check it out. You can see that there's something going on there. It kind of looks like a gas maybe going across the sky. And that's actually what it is. When a shooting star hits the atmosphere, it heats up the gases, and you get this envelope, if you will, of really hot gases that can be seen in ultraviolet. X-rays are going to show the hottest, no, not the hottest, but very, very, very hot gases. And they do not penetrate Earth's atmosphere, luckily for us, so it's got to be a space-based telescope. They will do some with where they'll put a rocket up into low altitude, or low altitude for space, but still it's really, really high, maybe 100 miles or more. They'll launch high-altitude balloons and make measurements this way, but the best are the space-based telescopes. They're just a lot more expensive. The upper left picture is our sun, and then to the right of that, of course, is Saturn. And you can see that Saturn emits X-rays, and they're coming mainly from the planet itself and mostly close to the equator, or closest to us, pointed toward us. So that allows you to delve into what is going on inside the planets, what process would emit X-rays. There's a galaxy on the bottom left. M31 is something that you can see with binoculars as a fuzzy patch. And there's two images there, one in X-ray and one in ultraviolet, and you can see that it's a little bit different than what you would see with the telescope, especially the X-rays. With the X-ray portion, you can see that there is something going on outside of the galaxy just above it. And that's actually part of the galaxy. It's not in the background or the foreground. So that led them to look for other structures of galaxies, including our own, which which we can't see at all. But we can see it in X-rays and things like that. And we have found structures in our own galaxy with things like X-rays and infrared. The absolute highest energy are gamma rays. This allows us to study solar flares and black holes and supernova. There's something called an FR, or not FR. It's a fast gamma ray burst. Maybe it is FRB, but we keep detecting these gamma ray bursts, which means it's a massive burst of energy. It's something exploding in the galaxy that we can't explain. And in the last few years, we've started to pick up on identifying. We've seen and measured the gamma ray bursts. In the past, a telescope would detect it, and then we point the telescope over to see what caused it, and there doesn't seem to be anything there. They expected things like the center of galaxies or black holes or whatever, but they never see the same kind of area when they see these. But recently they've detected a few where they had a gamma ray telescope in orbit, and they were looking for these and were able to record start to finish. So it's giving us some ideas of what they are, but I'll tell you this, up until last year, they are the most, the biggest explosions in the galaxy. Universe. These things are explosions bigger than the entire energy output of the Milky Way galaxy, and they can last a few seconds. So, yeah, it's pretty intense. Now, I don't even have a picture of the next one, but there's a new type of observation. So it's hard to call it a telescope. Einstein's math predicted that gravity could be disturbed and we would have these waves spreading out like ripples in a pond called gravity waves. Up until last year, they have been purely hypothetical. Einstein himself said we will never ever be able to measure these. The technology is too great. They'd be impossible. But we have an observatory in Antarctica that has detected 2 or 3 now, and from what they found, the first one they realized it came from an area where they believe 2 black holes collided. These explosions make gamma rays look weak, and gamma rays are 10,000 times more energy than the light that you see coming from a light bulb. Something that would cause gravity to ripple across the universe in a way we can detect it, it's literally an explosion that shakes the core of the universe, the actual space that we're in. Space is not just up, down, left, right. It's an actual thing. So this one's really new and exciting, but in ways that it's exciting because we don't know what we're going to get from this. We don't know what fundamentals about the universe we're going to learn, and that's what this is all about. Now, there's a thing that you heard about in chemistry called spectral lines. You might have done put the spectroscope up to your eyes and looked at it. A spectral line is just the band of colors. So a rainbow is a bunch of spectral lines. And what astronomers can do in this top right picture here, the line going across the top, so the top image, would be the spectrum that you see from some light source like a star. If there's a dust cloud in between the star and us, you get gaps in the spectrum. And those gaps can tell you what that dust cloud is made of. Sometimes a star will cause the dust cloud to glow, and then we have what's called an emission spectrum. And that spectrum allows us to further figure out things like what temperature the cloud is and what it's made of and all sorts of things. So, this one down here, the very bottom, this is the spectrum from our sun. And those black lines you can see there, that's an absorption spectrum. So something has absorbed those, or they're just absent from the sun. And it was looking at these spectrum that they first discovered that there was an element in the sun that didn't match anything they had done on Earth. And they named it after the, I believe, Greek god of the sun, Helios. So this is actually how we discovered helium, was by looking at these spectral lines. Later we found it on Earth, but we find that we can literally see what other stars are made of, what elements there are from the spectrum. Another thing you can do with spectral lines is our Doppler shift. So we have an object, this red dot, and it's moving to the left. If it is emitting waves, it could be sound waves, light waves, moving to the left, the waves on the left-hand side of it are compressed. They pile up in front of it. If it's a sound, you would hear it as a high pitch. And on the back end, the waves are spread out. You would hear it as a low pitch. So a race car, meow, going from high pitch to low pitch, is the Doppler effect. It turns out that things in the universe, stars and stuff moving around, are also going to be shifted. If they are shifted low frequencies or low wavelengths, then it is what is called blue shifted, because the color literally is shifted toward the blue end of the spectrum. If it is moving away from us, it is red shifted. So the spectral lines are what we can use to determine the motion of objects. They will actually look at the the red shift and the blue shift of the spectral lines coming from the surface of the sun, and they can detect the pulsing, the shaking of the surface of the sun from this sort of thing. They can see how quickly the gases rise and fall on the surface of the sun. So that's kind of cool. Here's a thought, if you want to pause it and read it. This is something that we will do later. We'll talk extensively about this. This is a joke. If you don't get it, go back to what I said about red shift and blue shift and whether it's moving towards or away from. So astronomers will use all sorts of telescopes to look from gamma ray, X-ray, ultraviolet. By the way, everything except visible and radio is going to have to be done up in space or very, very high altitude using airplanes or balloons. Things down on the ground are where we can measure our visible or radio light. And that's all I can see showing you today.